Hello and welcome. How do you organize a space party? You plan it. And speaking of space, let's talk about finding the volumes of solids. Like that transition? Alright, we'll start with solids that are made by rotating a 2D region about an axis. For example, suppose we draw the region in the XY plane, as shown in figure 1. I've tilted the XY plane a little because we're about to pop out in 3D. If we take this region and imagine rotating it about the x-axis, the region would fill the solid that we see in figure 2. So it looks kind of like a megaphone or something like that, but filled in, right? Filled in with concrete. Not much of a megaphone if it's filled in. In any case, this kind of solid that's generated by rotating or revolving a 2D region about an axis is called a solid of revolution. So you might see in the textbook or online, that's what it's referred to as. Now the question we're going to ask is, how can we find the volume of this solid? So we have formulas for volumes of spheres, boxes, cylinders, cones, but this is none of those. So what can we do? Well, it turns out that we can use the same technique that we used to find the area under a curve. In other words, break your thing into small approximate pieces and then take the limit as the number of pieces goes to infinity. In fact, we're going to use this same technique to find the lengths of curves and surface areas of solids and to solve physics and engineering problems down the road. It's one technique to rule them all, you might say. But coming back to our question, what is the volume of this solid? We can start by breaking our region into approximating rectangles in 2D. So let's look at that. So in figure 3, we've got our region that is broken down into 4 approximating rectangles. And just a side note, these are using midpoints here, but you could use left or right endpoints. It doesn't really matter in the long run. And then rotating these rectangles to create approximating solids. So can you say what the shape of these approximating solids would be if we're rotating about the x-axis? So if you said cylinders, or more specifically, right circular cylinders, then that's correct. So let's take one of these rectangles and rotate it about the x-axis just to drive home this point. So if we rotate about the x-axis, if you think about what solid is going to be mapped out by that rectangle, it's going to be some kind of cylinder. Each little line of the rectangle that's perpendicular to the x-axis, when you rotate it around, is going to be a circle, and those circles then fill out the whole subinterval that the rectangle is on. So you can imagine like taking one of those, taking that x value that you plug in to get the function height. Let me back up a second here. So right here, if you take this x value, you plug it in to get the height of the rectangle. So take the midpoint, plug it in to get the height of the rectangle. And then you just take that line and rotate it around, you'll get some kind of circle. You can imagine filling out the whole subinterval here with all of those circles, and you'll get that cylinder. For the next rectangle, it's the same idea. You can take that rectangle, rotate it around, and you'll get another cylinder. And then another cylinder and another cylinder. So here we'll have 4 of these cylinders, but if we had used more and skinnier rectangles, we would have more and skinnier cylinders. And the more we use, the better our approximation. So we can use more and more and more, and in the limit, the sum of the volumes of the approximations approaches the volume of the true solid. Okay, so that's the general idea, but we're going to want to do some calculations. So to figure out how to do that, we'll need to come back to figure 7 and turn to the notes on page 2, and we'll give this a try. We can start by labeling the x values that divide up the subintervals. So let's call them x1, x2, x3, and x4. Notice, by the way, that this picture looks slightly different from the one we were looking at earlier. Before, we were looking at using midpoints. Here it looks like we're using the right endpoints. right? On this first subinterval, it's the rightmost x value that we're plugging in to get the height of this rectangle. So I'm plugging into the function to get the height of that rectangle. Then the next subinterval we're plugging in x2 to get the height of this rectangle. So it's slightly different, but in the limit, we know that those differences don't matter. Right endpoints, left endpoints, midpoints, it's all the same when you take the limit as the number of rectangles goes to infinity. All right, so let's focus on this first rectangle. What is the width of this rectangle going to be based on our convention? You said delta x. That's correct. That's usually what we use for the width of our rectangles, just like we did in 6.1, just like you do in Calculus 1. And can you tell me the height of this rectangle? If you said f of x1, then that's correct. So that's the width and the height of this rectangle. Now let's focus on when we take that rectangle and rotate it about the x-axis. So we're still looking at the situation where we're rotating this about the x-axis, just trying to figure out the algebra that was going to give us the volume of the solid, first of the approximations, then the true solid. So if we rotate this about the x-axis to get our cylinder, then when we think about cylinders, what is the formula for the volume of a cylinder? So if you said pi r squared h, that's correct. That's usually the volume formula that we use for right circular cylinders. You can think of it as the area of one of the cross sections of this, which are all circles. So that's pi r squared, where r is the radius, and then times the height, where in this case the height is kind of like a horizontal height. You could take this cylinder if you really wanted to and put it flat on the table, and then it's really the height. But in this case, the height is kind of like the width of the cylinder you could think of. But that's generally our formula for the volume of a right circular cylinder. So now, what is the radius of this right circular cylinder? So if you say that's the same thing as the height of the rectangle, then that's correct. That's just f of x1. What about the h variable, the height of the right circular cylinder? So that would be delta x. That would be delta x, the width of that rectangle, approximating rectangle. So our formula for the volume of this right circular cylinder, this approximating unit, would be pi times f of x sub 1 squared times delta x. We're just replacing the r and the h with what they are in this picture. Now you're going to get the same kind of formula for the next circular cylinder, the next cylinder, and the next one and the next one. And so you're going to be adding up then all of these volumes of the approximating cylinders, and that's going to give you an approximation of the true solid that's made by revolving the region between these curves about the x-axis. So here we're looking at these sum of the approximating solids, the sum of the volumes of these cylinders. Where here in figure 9 we have 4 of the cylinders, but in general we can say that we're adding up n cylinders, so that we can take the limit as n approaches infinity. So you'll have more and more skinnier and skinnier cylinders that better fit the solid that we're trying to find the volume of. And so in the limit, these approximating these volumes, these approximate volumes, are going to approach the true volume of the true solid. But when we take that limit, we know that this is by definition the integral, the definite integral. So the f of x, the x sub I turns into an x, the delta x turns into dx, these Riemann sums turn into the integral. So we have that we can find the true volume of the solid by integrating across our interval, so that's from x equals a to x equals b, from the left of our solid to the right of our solid, pi times f of x squared. Remember, this is like the area of one of those cross sections, right? It's like the area of one of those cross sections. If you think about all of the cross sections of figure 10 of the true solid, all of those cross sections are going to be circles. Because if you take any line that's perpendicular to the x-axis and rotate it around, you get a circle. So every cross section, every slice is going to be some kind of circle. And then the dx here represents the width or the height of each of those circles or circular cylinders. In the limit, it's infinitely thin for each one. But that reminds you that that's the other dimension of these cylinders. Okay, so you can think about this as kind of like adding up all of those cross-sectional circles and then getting the volume of the true solid. All right. Now, rotating a 2D region like we did caused the cross-sections to be circles, and that was just an effect of rotating that region about an axis. But what if instead we just made the cross-sections squares, say, rising above the xy plane? Well, here's what this would look like. So here's the same 2D region in figure 11, but instead of rotating this region about the x-axis like we did just a moment ago, what if we just forced these cross-sections to be squares? And you can see this square right here that's rising above the xy plane into the third dimension, into the z direction, although we haven't drawn the z-axis axis here. Excuse me. Here, if you did that for all of the cross-sections, if you made all the cross-sections these squares, the solid would look something like this. You would have small squares over to the right, getting to be bigger and bigger squares as you move to the left. And that's because your distance from the x-axis to the curve on top is at first very small, but then gets bigger and bigger as you move to the left. So those bigger distances are going to create these bigger squares. In order for it to be a square, this side of the square has to be the same as this side of the square. So you're just going to get bigger and bigger squares as you sweep from right to left. So to create this kind of a solid with a little bit sharp edges here, right? Not super duper sharp, but they're kind of sharp. They're not round or smooth or anything like that. And every single cross section is a square. So how are we going to find the volume of that? Well, to answer that, we can think about what our approximating solids would look like. So let's come back to this 2D version of the region. We'll take that region, we'll break it up into subintervals and then rise up little rectangles above each subinterval. If we think about if all of these cross sections are supposed to be squares, so they're all supposed to be squares, then in the first subinterval, we can think about that square that's going to be there at x1, or where x1 was in our previous drawing. And think about using that same square to fill out the whole subinterval. So just take that square, fill out the whole subinterval, and what we'll get is a box or a rectangular prism, to use in the math term. So with this rectangular prism, that's the approximating unit that approximates the volume, or will approximate the volume of our true solid in that subinterval. And oh, there's my x1, x2, and x3, and x4. Yeah, got to practice this part beforehand. All right, so here we're going to have delta x is our width of this box. You'll have your f of x1 as this other dimension of the box. What's that third dimension of the box? If you said f of x1, then that's correct. Whoops. That would be f of x1 because these are supposed to be squares here. So whatever this dimension is, this is the same as this dimension. So we have delta x, f of x sub 1, and f of x sub 1. And the way you get the volume of a box is you do length times width times height. You just multiply all three dimensions together. So the volume of this approximating box is going to be f of x sub 1 times f of x sub 1 times delta x. Or in other words, f of x sub 1 squared times delta x. And when you think about the f of x sub 1 squared, you know it's that because those are the dimensions of the cross-sectional squares, right? Those are the dimensions of the cross-sectional squares. So you're going to do f of x sub 1 times itself because we have squares here. Or you can think the area of a square is one of its sides squared. So this is one of its sides squared. All right, now we're going to have boxes for each of these 4 regions. And the more boxes, the more subintervals we use, the more boxes we're going to have, and the skinnier the boxes will be. And they'll approach eventually in the limit, as the number of boxes goes to infinity, the volume of the true solid. All right, so the sum of these f of x sub I squared delta x's will, in the limit as n approaches infinity, approach the integral as x goes from a to b of f of x now squared and then dx. So you can kind of see that inside of these integrals, you basically have the formula for the area of whatever the cross-section is. If the cross-sections are squares, well, then you're going to think about what's the area of those squares. Well, it's going to be f of x squared, if you think through it. Back when we were rotating our region about the x-axis and we were looking at the cross-sections were circles. And so inside the integral, we had the formula for the area of the circles, pi times f of x squared. So this method of, this kind of cross-sectional method, as we're going to call it, works no matter what kind of cross-sections you have. The approximating solids are always going to be what we're going to call right cylinders. Now here we're using the more general version of the term cylinder. So when we talked about the cylinders at the beginning, we mentioned that they were specifically right circular cylinders. That's one kind of cylinder that's like a can-shaped. But we're going to use the more general sense of the word cylinder, where you could just have some shape like this. And as long as all of the cross-sections are the same, as you go from one base to the other base, so from one like face right here to the other face, one flat face to the other flat face, if all the cross-sections are exactly the same, then the volume of such a cylinder is going to be the base area, whatever that is. For right circular cylinders, it was the area of a circle, pi r squared. For the boxes, it's going to be whatever the area is of one of those sides. Could be like a length times height kind of thing. Or when we had square cross-sections like a moment ago, we just said it was a side squared, so f of x squared, for example. And then times the width, times the distance from one flat side to the other flat side, from one base to the other base. So if the area of this like kind of peanut-shaped flat base is a of x sub I, then, and if this is delta x for the width of the cylinder, then the volume of that cylinder, we'll call that v sub I, is going to be the area times the width. It'll be the base area times the width. This is something, again, you can remember when you remember the right circular cylinder formula. You think of the area of the circle, pi r squared, and then times the height. It's kind of like maps out the whole cylinder. It's the same thing in general, for the general version of the word cylinder. So generalizing this to this cross-sectional method that works not just for solids of revolution, but also for cases where you are told exactly what the cross-sections look like. If we have x sub I as a sample point, and then a of x sub I is the area of the cross-section at that x value, whatever that is, a circle or a square. Circle, if you're talking about in an area sense, sometimes we call it a disk to talk about all of the inside as well, to distinguish it from a circle, which is often just talking about the outside curve. But here we're going to use them a little interchangeably. We might shift over to disk, though, if you hear that word pop out. So if a of x sub I is the area of the cross-section at x sub I, then the approximating solid on that subinterval, which is going to have a width of delta x, will be a of x sub I times delta x. Again, this is the volume of an approximating cylinder. So our approximate volume of all the cylinders would be the sum as I goes from 1 to n of a of x sub I delta x. Then when we take the limit as n approaches infinity, as our subintervals, our delta x's are shrinking down to 0 and our cylinders are getting more and more skinny, we get the integral from a to b of a of x dx. So you can see right there, the only thing you have to think about really when you have these, when you're trying to find these the volumes of these solids that have the same cross sections across your interval. So that could be solids of revolution or ones where you're given the cross sections, like we were told they were squares in one of the previous examples. Whatever those cross sections are, you just have to find the area of those cross sections and plop them into an integral and integrate across your interval. So that's a really nice and clean result that comes out of all these approximations. In the next part, we're going to use this formula that we came up with, the integral from a to b of a of x dx, to find the volumes of various solids of revolution and also solids where we're given the cross sections. Thanks so much for watching. See you in the next part.